Okay, so let's get right into it. We all know someone, or maybe it's even you, who relies on a medical implant. Think artificial hips, heart stents. They save and improve millions of lives. But for them to work long-term, they have to survive inside our bodies. And that's what we're talking about today. The incredible invisible armor that makes this possible, all thanks to a process called sputtering.
So, let's start with the big question, the central challenge. You think that once an implant is in, the job is done, right? But why is it that these amazing pieces of engineering sometimes fail, leading to more pain and more surgery?
Well, it turns out our bodies are a surprisingly tough neighborhood for any foreign object. Seriously, an implant is in a constant battle. It's fighting off corrosion from body fluids, it's dealing with the wear and tear from every single move we make, and it has to avoid being attacked by our own immune system. It's a total triple threat.
So how on earth do you protect an implant from all of that? The solution is just brilliant, and it's happening at a scale that's almost impossible to wrap your head around. Scientists have figured out how to give these implants a custom-made suit of armor, literally, one atom at a time.
And the technique is called sputtering. Now, forget everything you know about regular paint. The best way to picture this is like spray painting a surface, but instead of paint, you're using a perfectly even layer of individual atoms. It's a super high-tech process that builds a flawless, protective shield right onto the implant itself.
Okay, so let's break down how this atomic spray painting actually works. First, you take the material you want your armor to be made of, let's say a chunk of pure titanium, and you stick it in a vacuum chamber. Then, you just blast that target with super-energized gas ions. It's kind of like a microscopic game of pool, where the ions are the cue ball, smacking atoms right off the target. And finally, those freed atoms fly across the chamber and land on the implant, building up this perfect, ultra-dense layer.
And here's where it gets really cool. You can choose exactly what kind of armor you want. Scientists have a whole menu of materials they can use for sputtering, and each one has its own unique superpower. It's all about picking the absolute perfect shield for the specific job that implant has to do. So what's on this menu? Well, if you have an implant that needs to fuse with your bone, you might pick titanium dioxide, or TiO2, because it actually encourages bone to grow right onto it. Pretty amazing. But if you have, say, a joint replacement, you need something incredibly hard and slippery to cut down on friction. That is a job for titanium boron nitride, or TiBN. And if your biggest worry is corrosion from body fluids, you'd go with chromium nitride, CRN, for its unbelievable resistance to rust and decay. All right, let's zoom in on that TiBN coating for just a second. You see this number? 0.27. Now, on its own, it doesn't mean much, does it? But in the world of material science, this number is a total game changer. It represents an incredibly low level of friction.
So let's put that 0.27 into perspective. We're talking about the friction coefficient. And compared to just plain old uncoated stainless steel, a TiBN coating is unbelievably slick. For an artificial hip or a knee, this means everything moves smoother, there's way less wear and tear over the years, and you get far less harmful debris generated inside your body. That tiny number, it translates directly into a much longer, healthier life for the implant.
But it's not quite that simple. Just being hard isn't enough. There's a catch. You know, sometimes the harder something is, the more brittle it becomes. Think of glass. It's very hard, right? But it shatters in an instant. So the next big challenge for scientists was figuring out how to make these atomic shields not just hard, but also tough.
You see, the problem is something called internal stress. As these super thin layers get deposited, stress can build up inside the material. And if that stress gets too high, it can cause tiny, microscopic cracks to form. And a crack in your armor, no matter how small, is basically a failure waiting to happen.
So how'd they solve this? Well, one incredibly clever solution is to build the coating in layers. Think of it like microscopic plywood, or maybe even baklava. Instead of one single thick layer, scientists lay down stacks of different materials, each one just a few nanometers thick. So now, if a crack starts in one layer, it hits the boundary of the next layer and just stops. It can't go any further. The structure makes the shield both ridiculously hard and tough.
Okay, but that's not all. Another brilliant approach is to create a composite coating. And the analogy here is just perfect. It's like adding microscopic rebar to concrete. By mixing in a second material at the atomic level, like say adding vanadium to titanium nitride, you change the entire structure of the material.
This extra element helps relieve that dangerous internal stress and results in a coating with hugely improved fracture resistance. And just how strong are we talking here? How strong can these composite coatings get? Take a look at this number. Using that TiBN composite we just mentioned, scientists have hit a hardness of around 31.5 gigapascals. I mean, that is an absolutely staggering figure.
To give you some idea of what 31.5 gigapascals really means, we are talking about a level of hardness that rivals industrial diamonds. And get this, this isn't some big bulky diamond. This is a level of strength they achieved on a protective coating that is in some cases just a handful of atom stick. It's a truly mind-blowing feat of engineering.
Okay, so the science is awesome. Atomic spray painting, microscopic baklava, coatings as hard as diamonds, it's all fantastic stuff. But what does all this advanced technology actually mean for the people, for the patients who get these implants? Let's talk about the real-world impact.
So here's the bottom line. This invisible armor translates into very, very real benefits. It means implants that last much, much longer. It means less harmful debris floating around inside a patient's body. It means the body is way more likely to accept the implant without putting up a fight. And all of that, it adds up to fewer painful, expensive revision surgeries, and ultimately, a better quality of life for millions of people.
And that kind of leaves us with a fascinating final thought, doesn't it? We've seen how this tech is creating these super-powered medical devices. But if we can build perfect, diamond-hard armor at the atomic level for something as complex as a medical implant, just imagine, what else could we armor next? The possibilities are really something to think about.